Okay, we're off to the next chapter, which is chapter 17. In this chapter, we're going to talk about electrochemistry. Main focus will really be galvanic cells, but we're also going to talk about redox reactions and balancing redox reactions. So again, depending on maybe who you took for Chem 50, you might have various degrees of knowledge on this. So we're just going to go over some of the basics. We'll talk about balancing redox reactions just to make sure everybody's going to be starting sort of on the same page. And then we'll get into really sort of the heart of the chapter, which is more the galvanic cells and that type of situation. So electrochemistry really involves redox reactions, and redox reactions are oxidation and reduction reactions. They typically do occur together. So somebody gets oxidized and somebody gets reduced. There's several definitions of oxidation and reduction, mainly sort of in general chemistry aspect of it. We think of oxidation as something that has basically lost electrons, or somebody that loses electrons. When we think about reduction as somebody that has gained electrons. And really, the transfer of electrons, as you might know, is one of the three reasons why, for example, a reaction takes place. That's one of the three, forming water and also forming a precipitator, the other two sort of main reasons why any type of reaction sort of takes place. Redox reactions as a whole basically encompass your synthesis reactions, your decomposition reactions, your single replacement reactions, your combustion reactions. These are all typically redox type reactions that are occurring. We'll talk about a couple other definitions as we go through this of oxidation and reduction, which a lot of times we'll kind of use more in, let's say, an organic chemistry type situation. But mainly here, it's sort of our electrons. And sometimes people remember this, like Leo the lion goes grr, loss of electrons, oxidation, gaining electrons, reduction. Some people are fond of the oil rig, I suppose. Oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig, he goes grr. You don't have to choose in that situation. Now, one way that's really important, or one thing that's really important when we sort of look at redox reactions, is to really understand, what is being oxidized and what is being reduced. And the way that we typically do that is we do look at what is referred to as the oxidation number, our state. And really, we look at an element, for example, on the left-hand side of the arrow to the right-hand side of the arrow, and we try to think about what's happening, which is oxidation state or number, which is sort of ish like a charge, but not exactly the same thing. And we can figure it out. And really, a very easy way, if you're not sure what's being oxidized or what's being reduced, but you can sort of correctly sort of identify the oxidation states on both sides of the arrow, is you just use a basic number line. And on the right-hand side is usually positive numbers, left-hand side is negative numbers. Now, when somebody does lose electrons, they have more positive than negative electrons and more protons, and they typically will become more positive. So if you look at something like the oxidation state of something from the left-hand side to the right-hand side, and it's kind of moving to the right here, or the positive direction in terms of its oxidation state, then that substance is going through oxidation. Same thing happens when somebody gains electrons, they gain more negatives, so they have more electrons than protons, so they would be moving on the negative direction, and that guy would go through reduction. So you can very simply just follow the oxidation state as to which way it's going, and you can figure out what is being reduced. So let's talk a little bit about electrochemical processes here. As we will see in this chapter, because of this transfer of electrons, this sort of transfer of electrons will allow basically those electrons to go out and do some type of work. So very similar to how a battery works in your whatever, you got a battery in. If you look at the battery compartment, there's little wires in there, and as the redox reaction is happening with your batteries, basically electrons are going out through the wires, going out doing some type of work, running a motor, light, whatever it may be, and it's making that process basically occur. So we're kind of turning that into some type of usable type of energy to do some type of work. Now, if we look at this reaction here, a little synthesis reaction, which is a redox reaction, magnesium plus oxygen makes magnesium oxide, also a combustion reaction. If we look at the oxidation state of magnesium, it is going to be 0 in this case. And any sort of element in a sort of natural state, uncombined with anything else, will have an oxidation state of 0. That means oxygen here is in its natural sort of state. It would also have an oxidation state here of 0. When the magnesium, the oxygen get together, that is really when they sort of gain charges, and our magnesium is going to be +2. Our oxygen here is going to be -2. So if we just kind of roll on our little number line situation here, we can look at magnesium, which starts at 0 and ends at +2. It is moving in a positive direction, so it's going through oxidation. By the way, by default, as soon as you know that is going through oxidation, the opposite guy is having the opposite thing of happening to it. So this guy would go through reduction, but you could also do the same thing for oxygen, which is starting at 0 and ending at -2, which is moving in that direction and going through reduction. So very simply, just which way it's moving, the oxidation state, you can very quickly identify what is being oxidized and what is being reduced in this case. That is what we should expect to happen in this case, because as you know, right, typically when we take a metal like we did here and a non-metal together, it is typically the metal that should be losing the electrons and being oxidized. The non-metal is usually the one that gains electrons, which means it should be reduced. So if you have a metal non-metal situation, it's not too hard to sort of determine. We can take this reaction, for example, and split it off into what is known as half reactions. And there's two types of half reaction. There's an oxidation half reaction and a reduction half reaction. And in this case here, it's our magnesium going from 0 to +2, and it's giving off 4 electrons in this case, and this would be the oxidation half reaction. When we write the oxidation half reaction, our electrons are always on the product side, like they are being given off, and that is definitely where you would find them. Now our oxygen here is 0, is going to actually gain those electrons to end up as a -2, and this is what's known as the reduction half reaction. And our electrons are always found on the reactant side in this case. The number of electrons that is lost by somebody in the oxidation half reaction should be the same number of electrons that is gained by somebody else in the reduction half reaction. So it should be sort of like a perfect transfer of electrons. These are called half reactions because when you take them together, anything on opposite sides of the arrow that's the same can either cancel out or reduce. And the one thing that should always cancel out are the electrons. So whenever you're adding two half reactions back together, you should always make sure that the electrons completely cancel. Now, in certain cases, you may not have the same number of electrons in each half reaction, and that may require you to multiply one of the half reactions by a number, or even both half reactions by a common number. But you should always, before you add half reactions back together, should always make sure that there's the same number of electrons on each half reaction. So again, they should always be on opposite sides of the arrow, and they should always have the same number before you add them together. Everybody on the left stays on the left, so that's our 2 magnesiums plus our oxygen. And then our ions here are going to come together to make 2 basically formal units of magnesium oxide in this case. By the way, here it is balanced, and that's why we have 4 electrons, because each magnesium is going to lose 2 electrons, and there's 2 of them, and that gives us a grand total of 4 electrons. Just like here, there are 2 oxygens, and each oxygen will then gain a couple of electrons each, and that's why we have those 4 electrons being transferred. Any questions on that there? All right. We look at another example here. Again, calcium plus oxygen, so oxidation state 0, 0. Once again here, +2 and -2. So again, if you just roll your number line here, our calcium is starting at 0, ending at +2, so it's being oxidized. our oxygen is starting at 0 and ending at -2, so it is being reduced in this case. So oxidized and reduced. Once again, here we have our balanced half reactions as being our oxidation half reaction, our reduction half reaction. And once again, if you add everybody together, our electrons should completely cancel out to give us our overall reaction that is happening here. Now, again, we have a metal and a non-metal, which is really good because we should know what's being oxidized and what's being reduced. But sometimes we don't have, for example, a metal and a non-metal. Let's just say, for example, we had this and this. And in terms of the iron, what is happening? Is it being oxidized or is it being reduced? So if we look at the iron's charge here on the left, it is going to be a +3. And over here, it is going to be a +2 as chlorine is -1 or chloride's -1 in each of those cases. So really our iron is starting over here at like +3 and it's ending at +2, which means it is moving in the negative direction and it is being reduced in this case. So again, it's a very simple way to sort of figure it out if you're not sure. All right, any questions on that there? Okay. Now, with that being said, in addition to looking at what is being oxidized and what is being reduced, sometimes we also look at what is considered what is known as the oxidizing agent or the reducing agent. And the oxidizing agent is always the substance that gets reduced. So it's sort of opposite of the name, while the reducing agent is always the substance that gets oxidized. So the idea behind this is it causes that in the other substance. So the oxidizing agent will get reduced, which means in order for it to get reduced, it's got to cause somebody to lose electrons. So if it causes somebody to lose those electrons that it needs, that's going to cause it to be oxidized. So it's known as the oxidizing agent. Same thing with the reducing agent is oxidized. When that thing gets oxidized, somebody's got to collect those electrons that it lost, and whatever collects those electrons that gets lost there will then get reduced. So that is, again, a different sort of question than what is being oxidized or what is being reduced. When you're asked about the oxidizing agent or the reducing agent, again, that is a different sort of situation. So if we looked at our calcium and our magnesium in the previous examples there that we looked at, this was being oxidized, which means the calcium here would be our reducing agent in that case. This was being reduced, which means this would be our oxidizing agent, and is actually the same on the bottom here as well. So when you're asked again about the agents, they're opposite of sort of the name. And again, it is a different question than what is being oxidized and what is being reduced. By the way, your oxidizing agent and your reducing agent are always found on the left-hand side of the arrow. It should be your reactants. That should not be your product. So if you're asked to specify what is the reducing agent and oxidizing agent, you should be very specific on what you're talking about because the elements on both sides of the arrow. So you should talk about what substance it really is in the particular case. Now, as I mentioned before, there are some other sort of definitions of oxidation and reduction, although we don't really use it too much in here. We'll just talk about it here so that you're familiar with it. So oxidation and reduction, there's kind of three basic definitions of each of those. As we talked about, losing electrons for oxidation, gaining electrons for reduction. Another common oxidation definition is somebody that gains oxygen as it goes from reactants to products, or for a reduction is somebody that loses oxygen as you go from reactants to products. And the last sort of definition is something that loses hydrogen as you go from reactants to products, or gains hydrogen for reduction as you go from reactants to products. So I would say, again, sort of these definitions here a lot of times are used in organic chemistry, because in organic chemistry, we're dealing with a lot of non-metal sort of action. So it's sometimes easier just to follow if somebody sort of gained or lost hydrogen or gained or lost oxygen along the way. So if you continue on to organic chemistry, there's definitely are some definitions that you will probably see again. I will say, like I said a second ago, probably here in general chemistry, these are going to be kind of your major definitions and stuff that you look at, but you can still use it. So, for example, if we look over here, the tin on the left-hand side has oxygen. The tin on the right-hand side has no oxygen. So it really lost oxygen along the way, which means that is a definition of reduction. The carbon by default would then be the oxidation sort of situation that's happening. But we could also look at the carbon on the left and carbon on the right has gained oxygen. So that is definitely a definition of oxidation. So that means in this case, our carbon would be our reducing agent. Our tin 4 oxide over here would be our oxidizing agent in this particular case. Now, in this case, we actually do have a metal we could look at, and even if you weren't sure about those other definitions, you could still just use like the metal to help you figure it out what's going on. Again, the tin here is a +4, and over here our tin is 0. So if we roll up there on our number line, we're starting at +4, we're ending at 0. We can see is becoming more negative, so it's going through reduction. So as soon as you're able to identify this guy going through reduction, by default, again, the other guy has to go through oxidation. So that's one of the sort of the nice things about redox reactions is if you frankly could just for sure identify what's happening with one substance, by default, the other thing should be happening with the other substance. Any questions on that there? So speaking about sort of identifying what's going on, being able to correctly identify oxidation states and numbers are really important in just basic redox reactions, but also really important in terms of when we talk about galvanic cells a little bit later on and some other things to really understand what is being oxidized and what is being reduced. So the main way that we sort of look at that is by looking at oxidation number, our state, and this is sometimes referred to as oxidation state. And the oxidation number is the charge the atom would have in a molecule or an ionic compound if the electrons were completely transferred. So the first rule of assigning oxidation numbers is, as we saw there in a couple of those examples, anything that is a free element, how it naturally comes uncombined with anybody else, will have an oxidation state of 0. So any metals by themselves, not attached to anything, oxygen, nitrogen, hydrogen, those type of guys, and their sort of standard states will also be 0. In a monoatomic ion, the oxidation number will equal the charge. So if you have a lithium ion, it's +1. If you have an iron 3, it's +3. Oxygen, I would say, when you're assigning oxidation numbers, is usually a fairly good place to start at. And that is going to be usually a -2. Now, although oxygen is usually -2, there are a few cases or a couple of cases you might come across where it is actually not oxygen, but it is peroxide, which is O22 minus. So that is peroxide right there. And in that case, the oxidation state there would be a -1. How do you know it's peroxide versus oxygen? I would say sort of that extra 2 sort of hangs out there as well, as opposed to sort of oxygen. So you usually have that extra 2 sort of happening. And again, this would be -1 and +1 in terms of oxidation state. I would also say that probably 9 times if you see an oxygen, it's probably just oxygen by itself. But again, occasionally could be peroxide, so you just got to keep an eye out on that. I would say hydrogen peroxide, sodium peroxide sometimes are common ones that you come across. The oxidation state of hydrogen is going to be +1, except if it does come in a binary compound after a metal, and then it's really hydride, which is -1. So if you had LiH, then the oxidation state of hydrogen would be -1 in that particular case. Everybody in group 1 and group 2 are their normal sort of charges / oxidation numbers. So +1 and +2 for those guys. fluorine is always -1. Now, when you add up the oxidation numbers for everybody, they do need to equal the overall charge on the molecule. So if that is a neutral molecule, when you add up all the oxidation numbers, they do need to equal 0. If it is some type of like polyatomic ion or something like that that does have a charge, then it does need to equal the overall charge when you add it together. So if we look at something like our HCO3 minus, which is our bicarbonate, I would say if you have a situation like this, sort of a 3-pack of elements, and you want to figure out the oxidation numbers, usually you kind of go right, go left, and keep the guy in the center for the end, and that's usually a good way of doing it. So we'll start with oxygen, which is -2, and there are 3 of them, which really gives us kind of a grand total of -6 there for our oxygen contribution. Our hydrogen here would be +1. Now remember, in this case, it does have an overall charge, which means when we add all those together, we do want to end up at a -1 overall. And that means that the carbon here does have a +4 situation, I believe. And that's going to give me 5 minus 6, which is -1. And when we do give, though, the oxidation numbers are the oxidation states, we would write something like hydrogen here would be +1, carbon would be +4, and oxygen would be -2. It would not be -6. It's not the grand total. So when you are stating oxidation states or numbers, it is just like one of them by itself. You also should include the charge, both on positive and negative guys, when you give the oxidation number. So you shouldn't just lay up like a 4 or something like that. So you should do +4, -4, or whatever it may be. So you should include the positive signs and the negative signs when you're doing oxidation numbers or states. Any questions on that there? All right, so why don't you try these for each of them, give the oxidation states for each of the elements involved. So take a few moments there and correctly identify our oxidation states of each of the elements involved. Okay, so let's take a look. We'll start up here at top with our lithium oxide. Start with oxygen, which is -2. And again, to balance that out, obviously our lithium here would be +1, and our lithium has an oxidation state of +1, oxygen here being -2 there. Coming over here to our PF3, in this case, our fluorine does need to be -1, so there are 3 of them because it's a -3. So our phosphorus in this case is actually going to take on a +3 oxidation state. So phosphorus here would be +3, fluorine here would be -1 in this case. Coming over here, we have 3 of them, so I would start with the oxygen, which is -2, so that's going to give me -6, a little +1 action there. In this case, it does equal 0, so the nitrogen here would actually be a +5 oxidation state. And lastly, so our hydrogen +1, nitrogen +5, oxygen -2. Our oxygen here going to be a -2. That's a -14. It does need to equal -2 overall. There's actually 2 chromiums here. So do a little math problem. Each of the chromiums does need to be +6 in this case. That gives us a +12 -14 equals -2 basically happening. And again, here our chromium would be +6, not +12. Oxygen would be -2, again, not -14 in this case. Yeah. Any question on any of those? So a reminder that the oxidation state and number is not necessarily the charge that you associate with certain elements in an ionic compound. If it is an ionic compound, it will have those because electrons are being completely transferred. But for example, in the case of phosphorus, where we normally think of it as being -3 because it's group 5, and it's actually going to take a more positive oxidation state in this case because it's actually sharing electrons. And based on electronegativity, these guys are way more electronegative, which means it's going to drag the electrons away from the phosphorus. And because it's sharing electrons here, it will take on a more positive oxidation state rather than the normal sort of -3 when it sort of accepts it from a metal in that particular case. And the same thing here, if you look at your sort of nitric acid, it looks something like this. And same idea here between nitrogen and oxygen. Oxygen is more electronegative. So again, it's going to kind of suck those electrons away from the nitrogen. And again, instead of being its normal sort of -3 sort of charge in an ionic situation, whereas to receiving the electrons, in this case, is sort of having the electrons being kind of dragged away as it's sharing electrons. So when we're dealing with elements that are basically sharing electrons in a more covalent bonding situation, that electronegativity makes a big difference in sort of their oxidation states that they would have. Any questions on that there? Again, obviously making this guy more positive. All right, so now that we know how to properly assign oxidation states and a little bit about basic redox reactions. Now, regular sort of simple redox reactions and half reactions, as we talked about earlier, you pretty much, before you add them back together, just need to make sure that you have the same number of electrons in each half reaction. And as I mentioned before, it may require you to multiply one of the half reactions by a number, both of them by a number, or not has to do it at all, and just add them together because they have the same number. Now, when we're balancing redox reactions in a little bit more complicated sort of situations, in either acidic or basic conditions, there's a few things that we do need to do that's a little bit different. And we're going to talk about acidic conditions first, and then we'll talk about how to kind of switch it over from acidic conditions to basic conditions. So really the first thing, if we were going to look at this here, our iron 2 plus our dichromate, one of the first things that you probably want to kind of think about is what is happening, what is being oxidized, what is being reduced. So if we look at the iron here, it has a +2 charge. Iron on the other side is +3. We just did this guy, that is +6 for our chromium, -2 for our oxygen, and +3 here for our chromium on the other side in terms of oxidation states. Once again, we can very simply just use our number line if you're not sure to see what's happening. We look at the iron here, it's starting at +2 and it's ending at +3, which means it's actually becoming more positive and is going through oxidation. So this guy here is going through oxidation. And by default, that means that this guy here would go through reduction. But once again, we could also do the same thing for that, starting with our chromium, which is like +6, kind of in this area. And it's ending at +3, which means it's moving in the more negative direction and going through reduction, right? Now, that would also mean in this particular case, my oxidizing agent would be which thing? Oxidizing agent would be the dichromate here would be my oxidizing agent. This would be my reducing agent in this case, because again, it's opposite basically of the name. So once we have sort of figured out what is going on, that's really a great thing to sort of know, because it could help make sure that later on you didn't kind of screw up as you're doing this. So the next thing that we want to do is we want to really break these guys off into two half reactions. And one's going to be our oxidation half reaction, one's going to be our reduction half reaction. How do you break it off? You just simply take the elements that are the same on opposite sides of the arrow and put them together. So these are the two irons. The other guy has some chromate in there, our chromium. And these are our two half reactions, as we just identified. That's our oxidation, and that is our reduction half reaction basically happening. Once you have split off the equation into its half reactions, the next thing that you want to do is balance everything. So we're going to split into half reactions, balance all elements except hydrogen and oxygen. So we're just going to balance any element that needs to be balanced, like a normal coefficient type balancing situation. So we have one iron on each side, so we're good. We do have two CRs on the left and only one on the right, so we do need to put a 2 there to balance out the chromium, because when we're done balancing these reactions, they do need to be balanced in really two ways. They need to be balanced like a normal chemical reaction, which means that you have the same number of elements on each side of the arrow, and they also has to be balanced in terms of charge. So you have the same charge on each side of the arrow. So actually has to be balanced in two ways. Once we do that, we can then move to really balancing the oxygen. And the way that we balance the oxygen is we actually use water. So we use water to balance the oxygen. Now, because we use water to balance oxygen, we're not just adding oxygen with water, but we're also adding hydrogen. So we need to the other side, add 2 H pluses for every water we added. So for example, the top half reaction has no oxygen, so we don't have to worry about it. The bottom half reaction, there are 7 oxygens on the left, which means to balance it out on the right, we would need 7 waters to add the 7 oxygens. But once again, here we just added with that water 14 hydrogens, which then need to come to the other side to keep everything balanced. So we add water to whichever side needs the oxygen. And then to the opposite side of you added water, you add 2 H pluses for every water that you added, and that will make sure you have the right number of hydrogens. Now, if you do come across a half reaction where there actually is more hydrogen to start with at the very beginning, and you kind of see extra hydrogens on one side versus the other, you could add the equal amount of H plus to the opposite side to balance out the hydrogens to begin with. At some point, you'll have to add some H plus to balance out that hydrogen. If you sort of run unbalanced with hydrogen to start with, just go to the opposite side, add the appropriate number of H pluses to do so. Now that we have balanced the oxygen and the hydrogens here, the next thing that we want to balance is actually the charge on each side. And we're going to balance the charge by adding electrons. So since electrons are negatively charged, we have to add it to whichever side needs the negative charge. The goal here is to end up with the same charge on each side of the arrow. It does not have to be 0 on each side. It just needs to be the exact same number on each side of the arrow. So if we look on the left-hand side, and really the easiest thing to do is just take the overall charge. That's a +2. That's a +3. So on here, the right-hand side will need 1 electron to balance out the charge. That'll give me a -1, which gives me an overall +2 on the left and +2 on the right. Now, when we look over here on the left, this is a +14. This, by the way, is a -2. There's no need to go individually by each element because the overall charge adds it all up for you. So why reinvent the wheel? That's going to give me a +12 on the left. That's 2 times +3 is +6, and that is 0. So in this case, we actually need 6 electrons on the left-hand side to balance it. And that will give me a -6 and a +6 on the left to match the +6 that I have on the right. Any questions on that there? Okay, so again, this is also the part of the program here where I'm just going to kind of clear out some of this here. It's important to know what is being oxidized and what is being reduced, because you could kind of check yourself to make sure you are adding the electrons in the correct sort of side, if you will. And we know that because in this particular case here, we identified this as the oxidation half reaction, which means my electrons should be on the product side, and it is. This was the reduction half reaction, which means my electrons should be on the reactant side, which it is. So if you ever find yourself adding electrons to the same side, that is definitely wrong because they should always cancel out. And again, this is a way you can kind of check to make sure you at least added the electrons to the correct side. Any questions on that? Now we're ready to add these back together, but before we can do that, we do need to make sure that we have the same number of electrons in each half reaction. And in this case, we have 6 here, but only 1 here. That is going to require us to multiply the top half reaction by 6 And I'm just going to write it underneath. So I'm going to go with 6 of the iron 2 goes to 6 of the iron 3 and 6 electrons. Now I am ready to add these back together. My electrons on opposite sides of the arrow, once again, should always completely cancel out. And then pretty much everybody on the left-hand side of the arrow stays on the left-hand side. Everybody on the right-hand side stays on the right-hand side. So that's going to give me 14 H pluses plus 6 of the iron 2 plus a little dichromate. On the right-hand side of the arrow, 2 of the Cr3 plus 7 waters and 6 of the iron 3. Now, if I did this correctly, this should be balanced in acidic conditions. So the way we want to check is like a normal equation, same number of elements on each side. I got 14 hydrogens, 6 irons, 6 irons, 2 Cr2s, 2 Cr2s, 7 oxygens, and 7 oxygens. Now, overall charge, I got a plus 14, a plus 12, and a minus 2. So that's like a plus 24 happening, I think, on the left, if I added that right. And on the right-hand side, we have a plus 6, a 0, and a plus 18, which I hope is a plus 24 as well. So we are balanced there, both in charge on both sides and also element-wise the exact same. Any questions on those steps there? Now, this is balanced in acidic conditions, and if you needed to balance this in basic conditions, there's multiple ways you could do it, but my recommendation would be to balance it in acidic conditions. And what you could do at this point is basically just turn it into basic conditions pretty quickly. There are other ways to do it kind of early on, but it's a lot of canceling out and stuff like that. So I think it's a lot easier to do it like this. So let's talk about if I want to turn this into basic conditions. And if I did, I'm going to erase some of this top part here and just recopy it up higher so we can see what's going on. I think some of those there. So after we balance it in acidic conditions, and if you did need it in basic, like I said, that's sort of the best approach, which is balance it in acidic conditions. And now that you have it in acidic conditions, what you could do is take your acidic equation. And again, I'm just going to recopy it up on top here. And we got here 14 H pluses plus 6 of those plus that. We got a couple of those. So now that I want to turn it into basic conditions, what I'm going to do is basically add OH minus to both sides. And it is equal to the number of H pluses I have. So however many H pluses I have, I'm going to add an equal number of OH minuses to both sides. So here I do have 14 H pluses, which means I'm going to add 14 OH minuses to the left. And I will also add 14 OH minuses to the right. Now, the side where you have OH minus and H plus and OH minus come together to make our friend water, right? A little H2O action. And at this point, usually what will happen is you'll have some waters you can cancel. So that's 7 waters on the left, can subtract out this 14 over here. That will leave us a net of 7 waters on the left, plus whatever else is left over at that point. And now if I again did this correctly without screwing anything up, I should still be balanced the same 2 ways. I have 14 hydrogens, 7 oxygens there, and 7 more make 14, along with 14 oxygens there, 6 irons on both sides, 2 Crs on both sides. Overall charge plus 12 and a minus 2 is a plus 10, right-hand side plus 6, plus 18, and a plus 14, or minus 14, sorry, minus 14. And that's going to give me a plus 10 on that side as well. So we are balanced in that conditions. So that would be my recommendation if you need to balance something in basic conditions. Frankly, just balance it in acidic conditions and then turn it into basic at the end. It is much, much easier. If you wanted to, you could actually do it before you add the electrons, but it gets a little kind of crazy. There's a lot more sort of canceling out that has to happen. There's a lot cleaner and easier way just to do it at the end. Any questions on that? By the way, how do I know the very first one I balanced was in acidic conditions? I see H plus, right? So that tells me acidic conditions. How I know the second one was basic? I see OH minus, yeah? So when you see that H plus, it's acidic conditions. You see OH minus, there's basic conditions. So that's a good way to kind of know that you ended up hopefully in the right spot there. Again, kind of tells you it's basic, and that kind of tells you it's acidic. Any questions on those steps? All right, so why don't we try a couple? Why don't you try one here? And again, we just want to make sure everybody's on the same page on these. Depending again on who you had, you might have did a lot of it or not very much. I'm not sure. Let's get here. All right, so why don't you try this one here? Let's balance this in basic conditions. See what you come up with. Also identify what's being oxidized, what's being reduced, the oxidizing agent, the reducing agent as well. All right, so take a few moments there. See what you come up with. Starting with our I minus plus MnO4 minus goes to I2 and MnO2. You might even see this reaction in about an hour. I don't know. Okay, let's take a look, see how you're doing. So again, I'm going to identify what is happening here. So our I minus obviously has an oxidation state of -1. Our MnO4 minus, our oxygen would be -2. That's a -8. Overall, it doesn't equal -1, which means the Mn here is actually going to be +7 in this case. And again, +7 and -8 will give us -1. I2 will be 0 as that's the standard state. Once again, here starting with the oxygen will be -2. That's a -4, which means here our Mn would be +4 in this particular case. Any questions on assigning those oxidation states? So with that being said, we can figure out sort of what's going on. And again, if you wanted to use the little number line approach, we can look at the I. I is starting at -1 here and ending at 0, which means it's moving in the positive direction, which means the iodine is going through oxidation. That means by default, really, our MnO4 is going to go through reduction, which we could also follow by +7. It's like out here, and it's ending at +4, which means it is moving in that sort of negative direction. And that means that it is going through reduction. With that being said, that means our I minus is our reducing agent in this case, and our MnO4 minus is our oxidizing agent. Questions on any of those identifications? All right, now that we sort of understand sort of what's happening, we're going to get into splitting this off into the half reactions. Just going to basically take the elements that are the same. So we got a couple of I's and Mn in the next one here. At this point, we do want to balance everything other than oxygen and hydrogen. And it does look in this case, we do need a 2 there for our I to balance it out. We have 1 Mn on each side, so we're good. Now we can move to oxygen and add water. Top one has no oxygen, so we don't have to worry about it. Bottom one has 4 oxygens there and 2 there, which means we actually need 2 waters on the right-hand side to give us the proper number of oxygens. Because we added 2 waters to the right, we then would need to add 4 H pluses there to the left-hand side. Any questions on that there? All right, now that we did that, we're off to electrons here. Overall here it is -2. Overall here it is 0. That means we need a couple of electrons there. And that's good because we did already identify this as our oxidation half reaction, which means our electrons should be on the product side. That means this is our reduction half reaction. That is a +4 and a -1, which gives us a +3. Over here, that is 0, basically. So left-hand side here, we'll need 3 electrons in that case to balance out the charge. That's going to give us, obviously, an overall charge of 0 when we do that. And that will give us 0 on both sides. And again, that also makes sense based on the fact that we are doing reduction there, and our electrons should be on the left-hand side of our arrow. Now that we have it, we're ready to add these back together. But once again, we can't do that until we have the same number of electrons in each half reaction. In this case, we will actually need to multiply the top one by 3. And we will also need to multiply the bottom guy there by 2 to get to 6 electrons in each. I'm going to dot line it, I think. And it's going to rewrite them both underneath, multiplying across. So that's going to give me 6I minus goes to 3I2 plus 6 electrons. On the bottom there, that's going to give me 6 electrons plus 8 H pluses plus 2 MnO4 minus goes to 2 MnO2 plus you plus 4 waters. At this point, we could add these together. Our electrons should completely cancel out, which they do, so that is good. That's going to leave us here. Everybody on the left stays there. 8 H pluses plus 2 MnO4 minus plus 6I minus goes to 3I2 plus 2 MnO2 and 4 waters. This should be now balanced in acidic conditions, and if that is sort of what I was shooting for in this problem, I would be done. I could put a box around it. We have 8 hydrogens on both sides, 2 Mns on both sides. We have 8 oxygens on both sides and 6 Is. Overall charge on the left there is 0, and overall charge on the right is 0. So this would be balanced in acidic conditions if I were done at that point. Any questions up to there? Now at this point, we're going to turn it into basic conditions. So remember, to turn this into basic conditions, we're going to take the number of OH minuses, which in this case is 8, our H pluses, which in this case is 8, and we're going to add 8 OH minuses again to both sides. That will create us 8 waters here on the left-hand side. And we can reduce that down by crossing it off there, kind of like subtracting. And that's going to leave us, I'll rewrite up on top here, 4 waters on the left, plus 2 MnO4 minus, plus 6I minus, goes to 3I2 plus 2 MnO2 and 8 OH minuses. And once again, here we should still be balanced. We got 8 hydrogens on the left and 8 on the right. We got 12 oxygens on the left, also 12 on the right. 2 Mns on both sides, 6 Is. Overall charge on the left there is a -8. Overall charge on the right is a -8. So we are balanced again both ways. Any questions on that there? Question on how to balance these type of redox reactions. Did we do this in Chem 50, a lot of it, or no? No, that's what I thought. All right. And then moved on very quickly. So I said, all right, then maybe we'll do one more just to make sure. All right, why don't we do, let's do this one. Why not? All right, one more here. Let's balance it in acidic conditions then. Okay, let's take a look. We're going to start kind of same idea. We're going to figure out what's going on. So we did this guy earlier. We had a +6 on that and -2. Here over at the oxalate, that's a -2 for the oxygen. It's a -8. We do need to equal a -2 overall. So that looks like a +3 action happening there. That'll give us a +6 and a -8 gives us a -2 left over. We have a +3 over here for our chromium. Oxygen being -2, -4, +4 there for our carbon in this particular case. Once again, if we just kind of follow what's going on, we take a look at our chromium starting at +6, which is out here, ending at +3, which means it is becoming more negative and going through reduction. We look at our carbon, which is +3, ending at +4, becoming more positive, going through oxidation. All right. So we know that that is being reduced. This guy is being oxidized. That would also mean that our oxalate is our reducing agent, and our oxidizing agent in this case would be our dichromate. Questions on any of that there? All right, now we got that all kind of worked out, we're going to split it off. So chromiums with chromiums in this case, and carbons with carbons, really, in this case. And again, this is going to be our reduction. That's going to be our oxidation. We're ready to balance everything other than oxygen and hydrogen. And in the top part there, it does look like we do need a 2 there for our chromium. We will also need, it looks like in the second one, a 2 there for our carbon as well. Now that we've done that, we're ready to add our water to balance out our oxygens. Top one, we got 7 oxygens on the left. That means we do need to add 7 waters to the right. Because we added in the 7 waters to the right, that's going to need to be 14 H pluses to the other side to make sure that we have our hydrogens balanced. Coming to the bottom one, actually, by adding the coefficient for the carbon, that also took care of the oxygen, so we don't need to add any water there to the bottom in that particular case. So now that we've done that, we're ready to balance out our charge with electrons. That's a +14. By the way, this is again the grand total of everybody. That's a -2. That's a +12 on the left. Over here's a +6. And this guy is 0. So looks like we do need 6 electrons over here on the left-hand side. Also works good because that is our reduction reaction. So that's the correct side to add them to. On the bottom, we got a -2 and we got a 0. That means we need a couple of electrons there on the right-hand side. Also good because that is our oxidation half reaction there. Any questions on that so far? Yeah. All right, we're ready to add them together, but again, we do need to always make sure we have the right number of electrons. And in this case, we do need to multiply the bottom guy there by 3 to get us to 6 electrons in each. And if we do that, I'm just going to rewrite just the bottom one. I think that will give me 3C2O42 minus 6 CO2 and 6 electrons. Just going to put a line through it now. And now we are ready to add these together. We got 6 electrons canceling. And I believe that should be it in terms of the cancellation. Everything on the left stays there. So 14 H pluses plus a Cr2O72 minus and 3 C2O42 minus. Everybody on the right will stay there as well. 2 Cr3 plus, 7 waters, and 6 CO2. And once again, if we did this correctly, this should be balanced in acidic conditions as we see H plus there. That's 14 hydrogens on the left, 14 on the right, 2 Crs on the left, 2 on the right. 7 oxygens plus 12 is a lot, but 19 maybe. And 7 oxygens and 12 is 19. 6 carbons on each side. Overall charge, that's a +14. That's a -2. That's a -6. You know, whatever that is there, plus 6, I think. And on the right-hand side, that is a plus 6, as these guys are zeros, right? In that case. So we are balanced again, both ways that we need to be, both like a normal equation, same number of elements on each side, and same charge on each side. Again, doesn't have to be 0, but just is equal the same charge. Any questions on how to balance these more complicated redox reactions? Right. So the key is it's good to figure out what's going on, and also just make sure you kind of keep track of things. Sometimes people recopy things and kind of mess up recopying and stuff like that. Obviously, you need to be able to balance these guys in acidic and basic conditions, be able to identify what is being oxidized, what is being reduced, what is oxidizing agent, a reducing agent, and be able to identify everybody's oxidation states. Any questions on any of that stuff there? Okay. I think we will lay it up then for today and go off.